Today we continue our study of industrial hydraulic technology with the hydraulic transmission of force and energy. In hydraulic systems, energy in the form of pressurized liquid flow is transmitted and controlled through a conduit system to an actuator at the point of work. Liquids have a few characteristics which make them an excellent means for transmitting energy. They take the shape of any container you put them in. They are relatively incompressible, and when a force is applied to a confined liquid, it is transmitted as pressure equally in all directions. This particular characteristic of liquids is called Pascal's law, named for the man who first discovered the relationship of force, pressure, and area. Pascal's equation looks like this. Pressure, usually measured in pounds per square inch, is equal to force in pounds divided by the area in square inches. Monitoring the pressure of the fluid is one way to determine how well the system is operating. Two types of pressure gauges most often used to monitor industrial hydraulics are the Borden tube gauge and the plunger gauge. A Borden tube gauge basically works on the same principle as this party noisemaker. It has a curved metal tube which has a gear linked to its end. Just like the noisemaker, when pressure is applied to the opening, the tube tends to straighten out. The more the pressure, the more it straightens. This movement then is transmitted to a second gear, which has a needle pointer attached to it. The needle, in turn, points to the pressure reading calibrated on the face of the gauge. Borden gauges are precision instruments, capable of readings as accurate as 1/10 of 1%. But they are relatively delicate, and the pulsations in most hydraulic systems could quickly damage them, unless some provision is made to isolate them when not in actual use. Sometimes a device called a snubber is used. It's installed in the line between the gauge and the system. It works by stopping or restricting fluid flow to the gauge, so any pressure surges or pulsations are smoothed out before they reach the gauge. The plunger gauge consists of a movable plunger connected to system pressure, a bias spring, a pointer, and a scale calibrated in pounds per square inch. As the pressure in the system rises, the plunger compresses the bias spring. As the plunger moves, so does the pointer connected to it, indicating the appropriate pressure on the calibrated face. While not as accurate as Borden tube gauges, plunger gauges are a more durable and economical means of monitoring system pressure. Now, to convert hydraulic pressure into mechanical force, we can use various types of actuators. The most common type of actuator used in hydraulic systems is the cylinder. Hydraulic cylinders take hydraulic pressure and change it into a straight-line mechanical force. This straight-line force is frequently called linear mechanical force. Hydraulic cylinders basically consist of a cylinder body, a piston rod attached to a movable piston, and a closure at each end. This is called the rod end because the piston rod goes through it, and this is called the cap end. Most cylinders have holes called ports at each end. The inlet port allows the hydraulic fluid to enter the piston chamber, and the vent port allows the fluid to exit. When a force is applied at point A here, the resulting pressure is transmitted to the piston in the cylinder. The pressure pushes on the piston, resulting in a mechanical force here at point B. Remember that one of the major advantages of hydraulic systems is that they can be used to generate large mechanical forces. Let's say we want to use 5,000 pounds to move a 7,500-pound load. Here, at the input end, we apply a 5,000-pound force on a piston with a 10-square-inch area. Okay, by applying Pascal's law, which says pressure equals force divided by area, we come up with 5,000 pounds of force divided by 10 square inches of area, which gives us 500 pounds per square inch of pressure in the system. So here, on the other side of the piston, we have 500 pounds per square inch of pressure pushing against this larger piston, which has an area of 15 square inches. Now, since we already know the pressure, we want to find the force here. Our equation becomes force equals pressure times area. So our output force is equal to 500 times 15, or 7,500 pounds. We are able to increase the mechanical energy of a 5,000-pound weight enough to move a 7,500-pound load.